So as we said that we're covering this chapter 3, matter and energy. So this is a start of basically chemistry in the real sense, you can say. So I can see that many of you have a very broad understanding of chemistry, but chemistry is really like, it is broad, but at the same time, it's really like everywhere, you know, everywhere, like not just on this earth, it's outside, it's in the cosmos, it's inside you, it's within you, it's inside the plants, it's inside the animals, it's inside the, you know, inside your, happening right there inside your telephones, it's happening inside the light bulb, you know, so it's everywhere, everywhere. Even when you're living, chemistry is there. Even when you die, your body, biologically, yes, you may die, you know, spiritually, yes, you may die, but chemically, you cannot die. You will continue to remain, you know, in, you know, atomic form, you can still be there. So that's the, you know, very interesting part of chemistry. Now I want to show you some really interesting things in the nature, okay, in the nature, where you will see chemistry. So let me just share my screen here. And right here you see is the, 1 minute. Oh, 1 minute. Okay, so where is that? Okay, this is, okay. Okay, first tell me, what do you see this? What is this you see? And you can just like unmute yourself and then talk and then mute again, like that. So what do you see here? Yes, guys? What is it that you see on the screen?
Sea glass.
Sea glass, yeah. So it's the glass that is, so I think people are communicating through chat, but now I can't see the chat. That's what I'm saying, you know, unmute yourself, say it, and then mute again. So that's where we'll go now, because I can't see the chat. Okay, so here's the thing. This is what you see on the screen is the, this is in Fort Bragg, the glass beach, and that is in California, of course. I think it's the northern part somewhere. So in the Fort Bragg, this, what they had, of course, this was a land which they were just trashing, all kinds of, you know, just dumping ground for all kinds of things. So yeah, glass is also, you know, is also a part of trash. And, you know, bottles, you know, beer bottles and all kinds of bottles were there, glass, you know, from your tumblers and pots and pans and so forth. They removed, this beach was a dumping ground. So they cleared the beach. They removed the trash, but they could not remove the glass because glass is hard to handle, right? When you start, so they left the glass. Now what happens is the waves came, and these waves, they took the glass into the ocean, and then again the glass pieces came back with the waves on the ocean. So they were like kind of, it's an agents of erosion were the waves, which kind of polished the glass with their, you know, movement. And as a result, the glass obviously became rounded, and it was like nice, beautiful marbles and all these different shapes. But at the same time, this glass is now you just strewn over. And I think now the people have taken away this glass. Many people have come just to, you know, take away the glass like a memorabilia, but still a very beautiful sight on that beach. And now the thing is that we're talking about the chemistry perspective. What is glass made up of? What is glass made up of? Just speak.
Sand.
Sand. So you take the sand, you start heating it. Okay, you take the sand, you heat it, and when you heat it, you know, obviously at some temperature, the sand begins to melt, and that's called the melting point. Okay, and this melting point of the sand is when it begins to convert from a solid to a liquid. Now, you start cooling it. Now, here's the thing. You take water, you cool the water, and it becomes ice, right? It becomes solid. So you take sand, you heat it, it liquefies, becomes a liquid. But when you cool it, you would expect it to become back into sand, a solid sand. But that's what it doesn't happen. In fact, it becomes glass. And so this glass is what we see in our lives, you know, we are using. So glass is like a liquid, basically, but it is going, it's solidifying, you know, it's slowly solidifying, and that takes years. So if you have seen some of these like historical buildings, you know, old architectural building, old churches, you will see the glass. Look at the glass. From the top, the glass is very soft, very brittle, but at the bottom the glass is thick. So what's happening is the glass is slowly, liquid flows, right? So the liquid is basically, glass is a liquid, so this liquid is basically flowing. And that's why you see it's slowly settling at the bottom. The thicker part is, you know, the bottom part is thicker, but the top part is smooth. You can also see the like these type of marks seen on the very, very old windows, very old windows, wood, because the glass is like sitting down. So that's the story with the glass, okay? Next is, I'll show you, yeah, that's very interesting. Now, what is this? What do you see here on the screen? Yeah, what do you see?
Rocket launch.
Rocket.
A rocket launch, yeah. And where is this rocket going? You know where?
Space. Into space?
Yeah, it's actually solar probe. So last year, they did the solar probe, right? They did the solar probe last year. And I don't know if it's the last year or year before last, I don't exactly remember, but here's an interesting thing. So we are looking for alternative forms of energy. So one of the alternative forms of energy is using the solar energy, not just the solar energy from the solar panels, no, but actually bringing the sun on this earth. What you have, what you see in the sun, actually having that sun on this earth. So that type of energy we are looking for. And that, where is that being conducted? Where is that being done? That is done in the nuclear reactors. And one of the things that we are working on is using nuclear fusion. So you are going to study this. One is nuclear fission, where they're splitting the atom, and that's producing energy. But now we are looking at that splitting the atom, that nuclear fission reaction is producing a lot of waste. And so nuclear waste is a big problem for us, how to handle that. So what we are doing now is we're taking two small nuclei of the hydrogen, which is like a baby of the elements, periodic table, really small, tiny atoms. You fuse them. The moment you fuse them, it produces massive amount of energy. So the kind of chemical reactions, not chemical, but it's a nuclear reactions that are happening in the sun. We are trying to bring the same nuclear reactions on the earth so that we can produce that level of energy that's being produced in the sun. But the problem is that's the whole infrastructure. So that's still in the stage, you know, it's still in the stage of research, but that's where the future is. If we are successful, we have, like, on a smaller scale, on a beta, you know, testing scale, we've seen some success, but on a larger scale, you know, we are still working on how to implement that on a larger scale. But if we are successful in that, then you know what's going to happen. All you need is one bucket of water, only one bucket of water, and that can suffice all your energy needs related to cooling your house, keeping your house warm, your air conditioning, your refrigerator, your kitchen, you know, appliances, washer dryers, you know, keeping the water hot, you know, your automobile needs, your telephone needs, charging, television, all your personal energy needs, right? All of those needs can be met for 30 years just from one bucket of water. So basically all you need is 3 buckets of water, and boom, you can live your entire life. Just 3 buckets of water, all your energy needs are going to be met. So that's like where the future is heading. And we have plenty of water on this. About 75% of the earth is water. So this solar probe is sent into, like, to study the sun, the solar flares, you know, the corona of the sun, you know, the atmosphere of the sun, and what else is going on in the sun. And so the thing that intrigued me was that, you know, sun has like thousands and thousands and thousands of degrees Celsius of temperature. So what thing can survive in the sun? Everything melts. The only thing, so it's on rockets, have to be made of something that can survive thousands and thousands and thousands of degrees Celsius of temperature. And that thing is carbon. So these rockets are actually made up of carbon outside and all. So when they go up, they can survive the high temperature of the sun, you know, so they're basically gone to gather data of the sun. Okay, so that's something very interesting, you know, so we are all looking at like all these different applications of science. Okay, so look at this one. This is amazing. What is this? You guys know this?
Those are the.
Is it the Northern Lights?
Yeah, Northern Lights, Aurora Borealis. Yeah, I can see now. Now from here, I can see the chat on my iPad from the side. Okay, so yeah, so these are the Northern Lights. So Northern Lights, such beautiful phenomena. Look at this one, and then look at this. So this is on my bucket list. At one point in my life, I want to see this, and it's just so beautiful. These are the neon signs of nature. Neon signs of the earth, you know, like how neon signs are beautiful, those advertising signs, same thing. So how did this happen? Very simple. Solar flares, solar, you know, winds, and so sun is giving away, you know, its own, you know, like electrons, and they come in this space and they strike the Earth's atmosphere, and then they hit the atoms that are present in the atmosphere. So these atoms have electrons. The electrons jump from a lower to a higher or higher to a lower. And when they do, they emit light. And this is this phenomenon. It's so beautiful. So chemistry is just so remarkable, you know. Then I'm going to show you like this piece right here. So remember I was talking to you about cheminformatics. So this is what I did, software. So now what we are doing is you're using the computer. We are designing molecules inside the computer. We are mimicking the environment inside the human body. So you see these ribbons, you see all these ribbons are the proteins. And these guys, these red circular thing, you know, with all these rings, this is a molecule. Organic chemistry, we show the molecules like this. So the molecules have shapes, the molecules have size, and the molecules have certain, you know, patterns, the way they kind of like arrange themselves. So when they are inside the human body, this is a drug candidate. So like drug candidate means it's a medicine. So how does this work? Once the medicine goes inside your body, it has to go and sit in the receptor region. So how can you make it sit? It has to be attracted to something in order to make it sit. So you see these dotted lines here? This is the very weak electrostatic attraction between these molecules and the molecules, the protein chains. So the protein chains and the medicine that you put, they kind of like connect, bolt together. And it's a very weak nuclear electrostatic attraction. The molecule is supposed to do what it is supposed to do. If there is excess production of something that is causing the disease, then the molecule needs to work on reducing that activity. On the other hand, if the molecule, if the body is not producing what some important thing that it's supposed, you know, so that if it's not producing that thing, and that's why you have a problem, a medical condition, then your molecule will, you know, create that environment in which the body begins to secrete that particular substance. So either way, the molecule, the drug candidate, the medicine, it will produce some kind of a therapeutic desired effect. And in order to produce that, it has to have some kind of attraction with its neighboring proteins. And everything is made up of in your body is proteins, right? So that electrostatic attraction. So we are going to study about that more. But generally, when you talk about chemistry, what do you see? You see test tubes, you know, you're working in the labs and you're working with chemicals, and you know, these chemicals have certain color. Yes, atoms, ions, they are all associated with certain very specific color, right? So here you will see all these different colors. Now, interesting part is the color you see is not the color that is being absorbed. It is the color that is being reflected. So all the other, white light is made up of 7 colors. So in this case, all the other colors are being absorbed except the violet color. Here, all the colors are being absorbed except the green color. All these colors being absorbed except the yellow color. You see that? So all these different colors that are being reflected are the ones the chemical is absorbing. Another thing is all these, there is a like yellow color is associated with iron. Iron has like bluish, orangish, yellowish color. Green is with nickel, and red could be strontium, or what is it? Maybe pink is for cobalt. Violet also belongs to something which I'm not remembering now. So, you know, white could be like magnesium. So all these colors also can be used to identify the particular atoms, right? Now, this is a very interesting one. I use this one for Chem 30A class, for my Chem 1A class, but here's the thing. This is your, these are oxygen, right? Do you see oxygen? Can you see oxygen? Yes or no?
No.
No.
Nobody, right? Nobody, yeah. So all those people who are answering, I can see it. So it's fine, you can answer chat also. So we cannot see oxygen, but you agree that you are breathing oxygen every living moment of your life. Yes or no?
100%.
100%, right? Everyone. If there is no oxygen, we would die, right? So so that's the beauty with chemistry. You do not see atoms, you do not see electrons, you do not see the gases, you don't see any of this, but still we have all these interesting phenomena happening because of all these, things. And we also, we have laws, we have experiments to prove that, so that's what makes chemistry very interesting, that you just have to believe it. That's all I'm going to say for now. Why? Because at some point there is a perfect logical proof, to support that theory, or that law or whatever. So here's this oxygen that you cannot see, right? You take the same oxygen that is in the gaseous form. Just let me just go back and show you. You take the same oxygen, you put it in the form of a the gaseous oxygen, you reduce the temperature, right? At room temperature, you can't see. But if you bring the temperature down, that same gaseous oxygen converts to liquid. So what you see on the screen is this liquid oxygen, blue color. You take that liquid oxygen and you just pour it. This is liquid oxygen. You're pouring it through the two plugs of magnet. Two plugs of magnet, north and south. You only know iron gets attracted to magnet, right? Here, that liquid oxygen is attracted to magnet. It is just remarkable, blows my mind. Liquid oxygen, in the gaseous state, it's not, but in the liquid state, it's attracted to magnet. So it's magnetic, But on the other hand, you take nitrogen, which is also a gas, the liquid, you can reduce the temperature, liquefy it, and then you pour it under the magnet, it just passes through. Oxygen is attracted to magnet, nitrogen is not. Why? So again, there is a lot of science behind it. So we are always looking for answers to the phenomena. So that, like electricity, right? Electricity. Why does electricity occur in nature? It's just when the positive and the negatively charged clouds, they collide, right? And boom, that's an electrical current. And we have all seen electricity. Unfortunately, electricity has been responsible for, I don't know if that's true or not, but for the wildfires, but that is what it is. But you see this one, amazing, beautiful. Fall season is so pretty, in especially, areas like North Carolina, South Carolina, Connecticut, just like it's so beautiful. But here also, we have some places where you still have those fall colors, right? But I think in Bay Area, spring is prettier. But anyway, this is the fall season. So what is happening here? Chemistry happening inside the leaves. Inside the leaves, you see chemical reactions happening. That is why the leaves are changing color from green to yellow to purple to orange and red and whatever, and then they start falling down. So that is a chemical reaction. Like it's more like what is it called? The phytochemical reactions, or like it's there, like the reactions that are happening in the plants. Okay, so here's the thing with nature. Nature loves chaos. Nature loves chaos. That is why we have volcanoes, we have tornadoes, we have storms, we have tsunamis, earthquakes, and this type of thing, what you see on the screen. Because nature likes to grow and grow in different ways. when there is a perfect chaos like this, then there's an opportunity for the nature to produce new things. So all these leaves that you see on the floor mean there may be some seeds also here and there. So that's when the seeds begin to, like, you know, combine and produce some new species of plants. On the other hand, all these dead leaves are not just dead leaves, they are nutrition. That's nutrition. They have nutrients. So if you just dump them in this, it becomes manure, and the plants can take the nutrition from them, you know. Not only this, like, you know, these days, I don't know if you guys are aware of it. These days they are making these forests. They're taking these forests, and these forests, you can go and you can sponsor a tree. In other words, you can have a family tree, and like all the dead, like once you die, you know, your ashes and all that can be given to the tree, like kind of like as a nutrition to the tree. So, and like you can have a family tree, and so basically, you know, those type of things. So anyways, the nature loves it. This is an example of entropy. Entropy is a term in science and chemistry where, you know, degree of randomness, the chaos, you know. So we're going to study more, but I just wanted to give you like a brief snapshot of what the chemistry is like. This is some of these experiments we do in Chem 1A, where these tubes, you know, these tubes have gases in them, and electrical current is passed through these tubes. And now they give out different colors. So this is actually a spectra. The spectra, so the colors, they reflect like which gas it is. So this, I believe, is helium, and like similarly, there's neon, there's argon, krypton, hydrogen. This is, I think, mercury. You know, so all these colors, they reflect these colors are are unique to the gas. Okay. Now here's something I want to show you on the screen. We talked about mind maps for your exams, right? We talked about mind maps for your final exam. So this is a very beautiful example of a mind map. Now this student, I mean, he really put his head, heart, and soul into it. He made like I have 100 pages of his mind maps. It's amazing, beautiful artwork, but not everybody is that artistic, you know, so, but still there's creativity, right? Whichever way you like those concepts to present those concepts, as far as you're showing some connectivity on this concept. So chemistry is not a linear subject. If you are thinking what we are doing in chapter 1 and it's not going to be in chapter 2 is not going to be in chapter 3, no, we're slowly building upon, you know, those. And then all these chapter 1 is 2 and 3 and 4, you'll continue to hit them in future chapters. So it's like that. So that's why it's very important you understand that all these different concepts have to be connected, and like keep that picture in mind. So this is an example of a mind map in which you're showing the connectivity of these concepts. This is another way, you know, he showed the connectivity of these concepts. It's amazing how he did that. So this